Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 4 for our MCAT Physics and Math playlist. This chapter is titled Fluids, and here we plan on covering 4 main objectives. In the first objective, we're going to begin by comparing fluids and solids, focusing on their defining properties such as density and pressure. Then we move into the second objective titled Hydrostatics. Here we're going to explore the principles governing fluids at rest, including Pascal's and Archimedes' principles. We're also going to delve into the molecular forces that dictate liquid behavior. Then we move into fluid dynamics. Here we're going to discuss viscosity. We're going to go over the differences between laminar and turbulent flow. And then we're going to see how these concepts connect to Bernoulli's equation. Then, in our last and final objective, we're going to apply our knowledge to biological systems, discussing how fluid principles underpin the functioning of the circulatory and respiratory systems. Now, with that overview in mind, let's go ahead and start with our first objective, which is titled Characteristics of Fluids and Solids. Matter, it exists in 4 fundamental phases: solid, liquid, gas, and plasma. For our purposes, we're going to be focusing on the first 3 phases of matter. Each phase exhibits unique properties that influence how substances interact with their environment. Solids, they're characterized by a definite shape and volume. They hold their shape because their particles are tightly packed in a fixed arrangement, which makes solids rigid and resistant to changes in shape or volume under typical conditions. On the other hand, fluids do not have a fixed shape. Fluids include both liquid and gas, and they conform to the shape of their containers. Now, the key difference between the two is that while liquids have a definite volume and are incompressible, gases can be compressed and they will expand to fill the volume of their container. Understanding these basic characteristics helps us distinguish between how fluids and solids respond to forces, which sets the stage for exploring more complex phenomena like pressure, buoyancy, and fluid flow. Now, as we move forward, keep in mind that the ability of fluids to flow and take the shape of their containers is fundamental to many of the principles that we're going to discuss in this chapter. Now, to understand the behavior of fluids, one of the most fundamental properties that we need to discuss is density. Density is a measure of how much mass is contained in a given volume of a substance. Mathematically, it's defined by the equation that you see here. Rho represents density, and density is equal to mass divided by volume. This relationship helps us understand why certain objects float while others sink. So, for example, a solid object like a stone is going to sink in water because its density is greater than that of water. On the other hand, something like a leaf is going to float because it is less dense. Now, the standard unit of density in the SI system is kilograms per cubic meter. However, depending on the context, you might find it more convenient to use grams per milliliter or grams per cubic centimeter. Now here I want to make a couple of notes. 1 gram per milliliter is equal to 1 gram per cubic centimeter. In addition, it's crucial to remember that for the MCAT, you need to have the density of water memorized. The density of water is equal to 1 gram per cubic centimeter, which is equal to 1 gram per milliliter, which is equal to 1,000 kilograms per cubic meter. So this is the density of water. Now, another key concept to grasp is how the weight of a substance is related to its density. The weight of a fluid can be calculated using this formula right here. In this equation, Fg is the gravitational force, the weight, and this is equal to rho, which represents the density of the fluid, multiplied by V, the volume of the fluid, multiplied by g, the acceleration due to gravity. Now, this formula is really useful in understanding buoyancy, which we're going to explore in more details later, but I want you to keep this equation in mind. Now, when we're comparing the density of a fluid to that of pure water at 1 atmosphere and 4 degrees Celsius, we use a dimensionless quantity called specific gravity. Specific gravity is defined as the ratio of the density of the substance to the density of water. Now, since it's a ratio, specific gravity has no units, and it's typically expressed as a decimal. For instance, a specific gravity less than 1 indicates that the substance is less dense than water and it's going to float, while a value greater than 1 indicates it is denser and it's going to sink in water. This basic understanding of density and specific gravity really helps us analyze complex fluid systems, and it helps us predict the behavior of different substances in various scenarios. Now, the best way to understand specific gravity is to tackle a practice problem. This one says, find the specific gravity of benzene given that its density is equal to 877 kilograms per cubic meter. Now, the ratio of the density of benzene to the density of water, that's going to give us our specific gravity. We're given the density of benzene, it's equal to 877 kilograms per cubic meter. We want to divide this by the density of water, and specifically, we want to use the density of water that has the same units as the density of benzene, which is kilograms per cubic meter. And we want that so that the units cancel out. The density of water in kilograms per cubic meter is equal to 1,000. So now we have 877 kilograms per cubic meter divided by 1,000 kilograms per cubic meter. Again, this is the density of benzene. This is the density of water. Taking this ratio gives us the specific gravity, which is equal to 0.877. And there we have it. We solved this problem. Now, another characteristic of fluids that we want to discuss is pressure. Pressure is defined as force per unit area. Now, for a given force, the smaller the area over which that force is exerted, the higher the pressure. The SI unit for pressure is Pascal, which is equal to newtons per meter squared. In other words, 1 Pascal represents 1 Newton of force exerted over 1 square meter of area. What's also important to note is that we're going to encounter different units of pressure, and we need to be comfortable and knowledgeable about how to convert between these different units of pressure. Common units of pressure that we're going to encounter is atmosphere, Pascal, bar, millimeters of mercury, and torr. Here you're going to see a bunch of conversions that you should familiarize yourself with. 1 atmosphere is equal to 101,325 pascals. 1 atmosphere is also equal to 1.01325 bar. It's also equal to 760 millimeters of mercury, and it's also equal to 760 torr. In addition, 1 torr is equal to 1 millimeter of mercury. So again, please look at these conversions that are summarized in this table and make sure you commit these to memory. Now, one important point to note is that pressure, despite being related to force, is a scalar quantity. This means it has magnitude, but no direction. And I know this might seem counterintuitive because force itself is a vector quantity with both magnitude and direction. The reason is that pressure is derived from the magnitude of the normal force, not its direction. So in a closed container that's filled with a fluid, pressure is exerted equally in all directions at any given point, irrespective of the orientation of the surface. This uniformity is due to the random motion of fluid molecules, which collide with the walls of the container and any surface within it equally in all directions. Now, to visualize this, imagine a container that's filled with a gas. The gas molecules, they move randomly and they collide with the walls of the container, exerting pressure uniformly in all directions. If we placed a flat surface anywhere inside the container, the pressure exerted on that surface would be the same regardless of its orientation. This is why pressure in a fluid is the same at all points at the same depth. And this is a principle we're going to explore further with Pascal's law. Now, understanding pressure is going to be essential in explaining various phenomena. For example, in respiration, air flows in and out of our lungs due to differences in pressure. When the pressure inside our lungs is lower than the atmospheric pressure outside, air rushes in. On the other hand, when the pressure inside the lungs is higher, air is expelled. This is also important when we discuss weather systems. Differences in atmospheric pressure create winds, and extreme differences can lead to storms and tornadoes. In engineering, understanding pressure is also extremely important. In construction and engineering, pressure differences are critical for designing structures that can withstand environmental forces like wind and water pressure. And these everyday examples highlight the importance of pressure in both natural and engineered systems. With that being said, let's go ahead and tackle a practice problem together. This problem says the window of a skyscraper measures 2 meters by 3.5 meters. If a storm passes by and lowers the pressure outside the window to 0.997 atmosphere, while the pressure inside the building remains at 1 atmosphere, what is the net force pushing on the window? Now, to calculate force, we can look back at our pressure equation. Pressure is equal to force divided by area. If we were solving for force, we can rearrange this equation to get that force is equal to pressure multiplied by area. Now, because the pressures are different on the two sides of this window, there's going to be a net force pushing on it in the direction of the lower pressure, which is outside the window. The difference in pressure itself can then be used to determine the net force. So our net force is going to be equal to our net pressure multiplied by area. This is equal to the pressure inside minus the pressure outside, and that's multiplied by area. Now we have all the quantities we need to plug values into this equation and calculate for the net force. The only thing I want to point out for us to keep in mind is our units. Force is expressed in units of Newton, which is equal to Pascal multiplied by meter squared. So we want to make sure that all our units are appropriate, that we calculate our net force in newtons. So let's go ahead and start plugging things in. Our pressure inside is 1 atmosphere. Our pressure outside is 0.997 atmosphere. We don't want atmosphere, we want Pascal, so we're going to apply a conversion. 1 atmosphere is equal to 1.013 times 10 to the 5 Pascal. This is going to be multiplied by area. We're given the dimensions of the window, the length and the width. Area is just length times width, so 2 meters multiplied by 3.5 meters. Now let's begin to simplify this a little bit so it's easy to calculate without a calculator. We'll start with this subtraction. This is pretty easy. 1 minus 0.997 gives us 0.003. Atmospheres cancel out. We're just left with this, 1.013 times 10 to the 5 Pascal. We can go ahead and approximate this to 1 and essentially just write 10 to the 5 Pascal. This multiplication is also really easy. 2 multiplied by 3.5 gives us 7 meters squared. Now, how can we simplify this a little bit more to make our calculation easier? We can rewrite this as 3 times 10 to the negative 3. And the reason we want to do this is because now we can focus on all of the values, 3 and 7, by themselves, and then focus on these exponents by themselves as well. 3 times 7 is equal to 21, and then 10 to the negative 3 multiplied by 10 to the 5, this is just equal to 10 minus 3 plus 5, which gives us positive 2. So then our answer is 21 times 10 to the 2 Pascal multiplied by meter squared. We can, of course, rewrite this to be equal to 2,100 Pascal multiplied by meter squared. This is equal to 2,100 newtons. So the net force here that's pushing on the window, that's going to be equal to 2,100 newtons. And with that, we can move into our next topic. To fully grasp the concept of pressure in fluid mechanics, it's essential to distinguish between 3 key terms: absolute pressure, atmospheric pressure, and gauge pressure. Let's start with atmospheric pressure. This is the pressure that's exerted by the weight of the Earth's atmosphere on everything at or near its surface. It acts in all directions, and it decreases with increasing altitude due to the reduction in the weight of the air column above. Now, at sea level, the average atmospheric pressure is 1 atmosphere. But depending on where you live in terms of altitude, you might experience atmospheric pressure a little differently. For example, people living in high altitude cities like Denver, they experience lower atmospheric pressure around 0.83 atmosphere. On the other hand, people living in low altitude areas like Death Valley, they experience atmospheric pressure that can be as high as 1.01 atmosphere. Now, this is important to note because atmospheric pressure has significant physiological effects, influencing processes like the boiling point of liquids and the oxygen binding capacity of hemoglobin in our blood. Next, we want to talk about absolute pressure. This is the total pressure exerted on an object submerged in a fluid. It includes both the atmospheric pressure and the pressure due to the weight of the fluid itself. And the formula for absolute pressure is summarized here. This equation tells us that absolute pressure is equal to 2 terms. This first term, P naught, is the ambient or surface pressure. This is often the atmospheric pressure, but I do not want you to make the mistake of assuming that P naught always stands for atmospheric pressure. In open air and most day-to-day situations, P naught is equal to 1 atmosphere, but in other fluid systems, the surface pressure may be higher or lower than atmospheric pressure. So this is our first term for absolute pressure. The second term is density of the fluid multiplied by the acceleration due to gravity multiplied by the depth of the object below the surface. So in short, absolute pressure is P naught plus rho multiplied by G multiplied by Z. Now that we have that mastered, let's discuss gauge pressure. Gauge pressure is perhaps the most commonly used form of pressure measurement in everyday applications, and it represents the pressure relative to atmospheric pressure, and it's given by the following formula. Here we see that gauge pressure is equal to absolute pressure minus atmospheric pressure. This means that gauge pressure indicates how much the pressure inside a system exceeds or falls below the local atmospheric pressure. For instance, when you use a tire gauge to check your car tires, the reading you get is a gauge pressure. A gauge pressure of 0 means that the pressure inside the tire is equal to atmospheric pressure. Now, if we replace our absolute pressure term with our equation for absolute pressure, we get the following equation. If P naught is equal to the atmospheric pressure, then the equation becomes P gauge is equal to rho multiplied by G multiplied by Z. This tells us that in such cases, the gauge pressure depends solely on the density of the fluid, the acceleration due to gravity, and the depth of the object in the fluid. This scenario is common when dealing with open fluid systems like a swimming pool or a tank that's open to the atmosphere where the surface pressure is the same as the atmospheric pressure. Now, to this point, gauge pressure can be either positive or negative. Positive gauge pressure indicates that the pressure inside the system is higher than the atmosphere pressure. On the other hand, negative gauge pressure indicates a vacuum or lower pressure relative to atmospheric pressure. Now, to summarize and connect the concepts we just discussed in regards to pressure, remember that atmospheric pressure is the baseline pressure exerted by the Earth's atmosphere. Absolute pressure includes both the atmospheric pressure and the pressure from the fluid itself. And gauge pressure is the pressure measured relative to atmospheric pressure, which is why a tire at 0 gauge pressure is not actually flat. It's just at atmospheric pressure. With that, let's go ahead and tackle a practice problem. This problem says a diver in the ocean is 20 meters below the surface. What is the gauge pressure at that depth? What is the absolute pressure the diver experiences? Side note, the density of seawater is 1,025 kilograms per cubic meter. Now, since the pressure at the surface, P naught, is equal to atmospheric pressure here, we can solve the gauge pressure by using this equation. P gauge is equal to rho multiplied by G multiplied by Z, where rho is the density of the fluid, G is the acceleration due to gravity, and Z is the depth of the object in the fluid. We have all the values we need to plug into this equation. Rho is 1025 kilograms per cubic meter. Acceleration due to gravity is 9.8 meters per second squared, and our depth is 20 meters. Now we can go ahead and round some of these values to make the calculation a little bit easier. I'm going to round this to 1,000. I'm going to round this to 10, and this can say 20. 10 times 20 is 200. 200 multiplied by 1,000 is 2 with 5 zeros. So that's equal to 200,000 pascals. We can rewrite this as 2 times 10 to the 5 Pascal. Okay, so that is the gauge pressure. We also need to figure out the absolute pressure that the diver experiences. The absolute pressure can be calculated by taking the atmospheric pressure and adding it to the gauge pressure. Now, the atmospheric pressure is 1 atmosphere, but we want to use it with the appropriate units, so not atmosphere, but Pascal, because our gauge pressure is in units of Pascal. 1 atmosphere is equal to 1.013 times 10 to the 5 Pascal, and we can add this with our gauge pressure that we just calculated, 2 times 10 to the 5 Pascal, and this gives us an answer of 1, I'm going to approximate this to 1 plus 2, that's equal to 3, multiplied by 10 to the 5. So our answer here for the absolute pressure the diver experiences is approximately 3 times 10 to the 5 pascals. And with that, we've answered the question. And we're going to go ahead and stop the lecture here. In the next video, we're going to continue with objective 2. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.